All right, today we are going to talk about the pendulum. Now, we talked earlier in a previous video about a mass on a spring and how it undergoes harmonic motion. But in that video, we also pointed out that the motion of a mass on a spring is analogous to many other things, like the motion of a pendulum at a small amplitude, or a ball rolling back and forth in a candy dish. So today we're going to specifically talk about the pendulum and how we can relate the motion of a pendulum to simple harmonic motion that we already studied in terms of a mass on a spring. So let's find the equation of motion for a pendulum. How do we find how a pendulum moves? Well, a pendulum, a simple pendulum, is simply a point mass connected to a string, which then is connected to a pivot point. Now, what is the torque, or what are the forces acting on our point mass? There's tension that is in the direction of the string, and then there's gravity pulling downward. All right? Now, we're going to do Newton's second law to figure out how this moves, but it turns out this is going to be easier to do if we do the angular version of Newton's second law, which involves torques instead of forces. So what is the net torque of this mass about the pivot point at the top? Well, the torque due to tension is zero because the tension is in the opposite direction as the lever arm. Therefore, when we do, RF sine theta, theta is 180 degrees, sine of 180 degrees is zero, and so the tension does not produce any torque. But gravity does produce a torque. Gravity produces a torque which is equal to mg times L times sine of the angle from the direction of the lever arm of the string to gravity, which is the same as this angle right here, the angle of the string from vertical, which we call theta. Now notice there's a minus sign here, and that's because if theta is positive, the torque is in the opposite direction. If theta is positive, the torque is in the negative theta direction to try and drive the pendulum back to theta equals zero, to the equilibrium point. Or in other words, if you use the right-hand rule, put your fingers downward and then rotate to theta, your thumb points out of the screen. So if that's positive, if that's the positive axis, then if we do put our fingers along the length of the string, or rotate our fingers into the direction of gravity, the torque due to gravity is into the string, or into the screen, which would be a negative torque. Now it turns out that the motion of a pendulum can actually be fairly complicated, so we're going to make a simple approximation. We're going to assume that we have small amplitude oscillations, such that theta never gets very large. Well, it turns out if theta is in radians, in the limit of small theta, sine of theta is approximately equal to theta. So we're going to approximate sine of theta with theta in our torque. Okay, so there's the total torque on our object, on our point mass, about the pivot point. Now we're going to use Newton's second law, which says torque is equal to moment of inertia, I, times alpha, the angular acceleration. Well, the moment of inertia for a point particle moving about an axis a distance L away is just ml squared. And of course, angular acceleration is just the second derivative of theta with respect to time. So torque is equal to this, but we know the torque, right? The torque is just negative mg L theta. So if we put that in for torque and then solve for the second derivative of theta with respect to time, we just get this. And notice that the m's cancel out. One of the L's on the bottom cancels the L on the top, and we just get negative g over L times theta. So there's our equation of motion. Now this is very similar to the equation of motion we got for a mass on a spring. For a mass on a spring, we said, the force is minus kx, and we plugged that into Newton's second law, and we got this equation of motion. And we said the solution to that is x equals a sine omega t plus phi, where a and phi are arbitrary constants, and omega was the square root of k over m. Well, for our pendulum, we found that torque was equal to negative mgl theta. Plugging that into Newton's second law, we got the second derivative of theta is equal to negative g over L times theta. And look, this is completely analogous. It's the same equation, except instead of having a function x, which is a function of time, we have theta as a function of time. And instead of having a constant here, which is negative k over m, we have a constant which is negative g over L. So the solution to theta ought to be the same as the solution we found over here, only in this case omega is going to be the square root of g over L instead of the square root of k over m. So groovy. We have an equation that describes what a pendulum does. So for small amplitude rotations, oscillations, a pendulum is simply going to oscillate sinusoidally in theta with an angular frequency of the square root of g over L. Well, if the angular frequency is the square root of g over L, then the frequency is just 2 pi, or omega divided by 2 pi, angular frequency divided by 2 pi, right? Where angular frequency is the number of radians per second, and frequency is the number of cycles per second, and that's just going to be 1 over 2 pi times the square root of g over L, right? Just take omega and divide by 2 pi. The period, the time it takes for a pendulum to do one oscillation, is just 1 over the frequency, and so that's just going to be 2 pi times the square root of L over g. Notice the mass didn't matter, as often happens when gravity is involved, right? Because the force due to gravity goes up with mass, the inertia goes up with mass, and it cancels out. So the period of a pendulum then just depends on the length of the string and gravity, right? But we've made some assumptions. This is a simple pendulum. It's a point mass connected to a string, and we're assuming small amplitude oscillations. So now we know our solution. We can plot and decide what theta should be as a function of time. So the y-axis is time and the x-axis is theta, and we see our pendulum just oscillates sinusoidally. All right, so here's an example problem we could do. I want to use a pendulum to time events. I want my pendulum to have a period of precisely 1 second. If I tie a string to an eyelet at the edge of a rubber ball with a radius of 2 centimeters, what should the length of my string be? Well, the angular frequency is g over L, and if I could find the angular frequency, I could find the period, which is what I want, right? So the frequency is just omega over 2 pi, or 1 over 2 pi square root of g over L, and the period is 1 over the frequency, so the period is just 2 pi times the square root of L over g. So what I'm trying to find is how long I need my string to be. So let's divide both sides by 2 pi and then square both sides, and we get this. Then if we multiply both sides by g, I can find an equation for L. But L is the length of it's the distance from the pivot to my point mass, right? And so I'm treating my rubber ball kind of like a point mass, which it isn't really. I'm going to get a better value for L if I let L be the distance not to the edge of the ball, but to the center of mass of the ball. All right, so instead of saying this is L, L is going to be from the pivot to the center of mass of the ball, which means the length of the string is L minus the radius of the ball. All right, and then we just plug things in, right? We want our time period to be 1 second. The radius of the ball is 2 centimeters, and we find then that the length of the string we want is 22.8 centimeters. Not hard to do. All right, so we talked about the simple pendulum, which is just a point mass connected to a massless string. Now we're going to talk about a physical pendulum. So a physical pendulum is some rigid object that is pivoting about some point. For example, imagine you carved a banana out of wood and painted it like a banana, drilled a hole in it, and then stuck a rod through so it could rotate around the rod. All right? It is, for small amplitude oscillations, it's going to undergo simple harmonic motion, just like a simple pendulum. All right? How can we find the angular frequency and the period of a physical pendulum? Well, what we do is we say, look, I've got this extended blob of mass. It has some weird shape, right? And then there is a pivot point right here that it's going to pivot around. There's only 2 forces acting on my object, the pivot and gravity. And gravity acts about the center of mass, all right? And so if we look for torques about this pivot point, right, the pivot won't provide any torque because its lever arm is 0. So the only torque will be caused by gravity, which acts at the center of mass of our object. So the lever arm for the torque is just the distance from the pivot to the center of mass of our physical pendulum, of our object. So the torque then is just negative mg times the distance from the pivot to the center of mass times sine of theta. All right? And once again, we're going to make the approximation that theta is small so that I can replace sine of theta with just theta. Then Newton's second law is torque equals I alpha, which is I times the second derivative of theta with respect to time. In this case, we're not going to plug anything in for I because it could be whatever it is, right? It's just I for this arbitrary blob of solid mass about the pivot point. That's the important thing to remember, though. It's the moment of inertia about that pivot point, because that's the pivot point we measured the torque around. All right, so if we solve this equation, if we plug this in for torque and then solve for the second derivative of theta, we get this, which again looks an awful lot like a mass on a spring. So the mass on a spring, right, we had a force, we had our equation of motion, we found our solution and said omega is k over m. For the physical pendulum, we have a torque that looks like this. When we use Newton's second law, we got this equation right here, which looks just like the mass on a spring equation, except instead of x as a function of time, we have theta as a function of time. And instead of multiplying our function by the constant negative k over m, we multiply by the constant negative mg L center of mass over I. So our solution is going to be the same, but with omega, our angular frequency, being mg L center of mass over I. Okay? Now, there's our solution as long as omega is equal to this. Now, if omega is equal to this, we can find the frequency. So omega is the angular frequency, the number of radians per second. I can find the frequency, the number of cycles per second, just by dividing omega by 2 pi, because there's 2 pi radians per cycle, per period. So there it is. And then we can find the period in seconds just by taking 1 over f. So there is the period. That's the time it takes for a physical pendulum to undergo one cycle. Now, the simple pendulum can be thought of as a special case of the physical pendulum. It's a physical pendulum where all of the mass is concentrated at a point. All right? And so the angular frequency of a physical pendulum is mgl center of mass over I. But for a simple pendulum, all right, L center of mass is just the distance down to the point mass, and the moment of inertia is just m L squared. The m cancels out, one of the L's down here cancels there, and we just get the same formula for angular frequency we got before for the simple pendulum. So you can just think of the simple pendulum as being a special case of the physical pendulum. All right, here's a problem we can now work. A uniform sphere with a radius of 8 centimeters and a mass of 4 kilograms has a small hole bored through it a distance of 2 centimeters from the center of the sphere. If I place a rod through the hole and start the sphere swinging with a small amplitude, what will the period of oscillation be? Well, omega is mg L center of mass over I. It's just the standard formula for the angular frequency for a physical pendulum. If I can find this, I can find the period. Well, to find this, I need to know the mass, and I need to know the L to the center of mass. Those are both given in the problem. And I need to know I. Well, what is I? Well, for a sphere rotating about its center of mass, it's just 5/2 mr squared, all right? And we know the radius of the sphere, that's given to us, all right? But what we want for I is not the moment of inertia about its center of mass. We want the moment of inertia about the pivot. So we're going to use the parallel axis theorem. So the I, moment of inertia about the pivot, is just center of mass moment of inertia plus m times the distance to the pivot, from the pivot to the center of mass squared, which is, for I center of mass, is just 5/2 mr squared. And then we have m, and then the distance to the pivot from the center of mass is L center of mass. So there's our I. And if I take that and plug it into the formula for angular frequency, I get this. Of course, the mass cancels out now. It turns out I didn't even need the mass. Not surprising, right? When gravity's involved, when gravity's all that's involved. Okay, now if I take the angular frequency omega and divide by 2 pi, I get the frequency. And 1 over the frequency is the period. So there's the period. I'm going to write this as 2 separate fractions, right? And it's kind of cool. You can see right here, what we get is basically what we got for a simple pendulum plus this extra thing right here. All right, so you can see the simple pendulum emerges out of the physical pendulum in the special case where I have a point mass, where r goes to 0. All right. Another interesting thing, what happens if the pivot is right going through the center of the sphere? What if it wasn't offset from the center of the sphere? That would mean that L center of mass was 0. So this term goes to 0, but this one goes to infinity, which means the period is infinite. And that makes sense, right? If I have a sphere and I drill a hole straight through the center and there's no friction, I get that sphere going, it's just going to keep going, right? It's never going to turn around and rotate the other way, all right? But if I offset that hole from the center of mass, now gravity provides a restoring force to make it swing back and forth. And if we plug in the numbers, I get 1.82 seconds. Okay, that is our discussion of pendulums. I hope that now you know all about how to make fruit rotate around wires and other such pendulum-related notions.